We can get current amplification at resonance, but we can't get power amplification. That current amplification occurs in the inductor and capacitor at resonance, which will amplify the source current. However, inductor and capacitor are passive devices, so average power is going to be zero in an inductor and capacitor. Additionally, we'll see when we look at the currents, the apparent power will actually be the negative of each other, so the total power will be zero. So let's take a look at the inductor and capacitor currents again at resonance, and we'll look at it through quality factor. It's easiest to understand through the quality factor. If you recall, our current through the capacitor at resonance is the negative of that through the inductor. So at resonance, our circuit looks completely resistive to the forcing function, in this case our current source. So all its current is going to flow through this resistor. All that current flowing through the resistor leaves us a voltage of R times I, that current phasor, that's the forcing function. So if we want to find the current through the inductor, we can just divide that by the impedance of the inductor, or 1 over j omega naught C. Again, omega naught, that's our resonant frequency, which is equal to j omega naught CR, and j omega naught CR, or RC, that's the quality factor at resonance. It's the negative of the current through the inductor, and you can show that that's going to be our Ri divided by j omega naught L, and you can show that that's also going to be j q naught times I, but it'll be a negative j. So if that quality factor is greater than 1, then we have current amplification. For example, if we have the magnitude of our current source here at frequency omega naught is equal to 2 milliamps, and we have a quality factor of 25, then the current through this resistor will be the 2 milliamps flowing downward, but the current through the inductor and capacitor will be 50 milliamps. That 50 milliamps is just going to be flowing around in this circle, in this loop, I should say, loop here, one being the negative of each other relative to the passive sign convention. So one will be absorbing energy while the other is delivering, and vice versa. And we get this pure resonance that we looked at the beginning of the resonance module. So if the Q of a circuit can be determined from its natural response, what we want to look at is the quality factor as opposed to some of its other characteristics. So resonance, again, that's associated with the force response of a circuit to a sinusoidal steady state forcing function. So what we've looked at is alpha, omega naught, and omega d. They're associated with the natural response. And we've looked at being able to determine whether we have an underdamped, overdamped, or critically damped response. Well, resonance is an underdamped response. So the two most important factors of resonance, however, are the quality factor and the resonant frequency. So these other factors, alpha and omega d, for example, we want to express them in terms of the quality factor and the resonant frequency. So if we look at our alpha for a parallel RLC, that was 1 over 2 RC. If we plug in for our resistance term, right, our quality factor is equal to omega naught RC. So R is equal to quality factor divided by omega naught C. The C's are going to cancel. We just end up with our exponential damping coefficient being the ratio of the resonant frequency to the quality factor, but it has 1/2 factor to that. So it's omega naught over Q naught times 1/2. Our natural resonant frequency, omega naught squared minus alpha squared, well, again, and for alpha, we can substitute our 1 over 2 Q naught squared. Well, we substitute omega naught over that, but we're pulling this out of the radical. So we have 1 minus 1 over 2 Q naught squared. So if we have a very high quality factor, this term is going to be very small, and our natural resonant frequency will be closer to our resonant frequency. So we'll explore that a little bit more later. But here we can express omega d in terms of omega naught and the quality factor, just by doing our substitution, starting with the fact that for all we've started with is that for a parallel RLC circuit, that our omega naught is equal to Q naught RC. Sorry about that. Let's correct this. Sometimes it's good to make a mistake, then hopefully you remember the right. So it's our Q naught, right? Our quality factor is equal to the resonant frequency times RC. That's all we started with. And then our damping ratio, that's the ratio between our exponential damping coefficient and our resonant frequency. So that becomes just 1/2 Q naught, or 1/2 of the inverse, the reciprocal of our quality factor. So these you should write down and remember. Let's take a look at an example using these new formulas that we have. If, for example, we have this parallel RLC circuit, and we know the inductance and the capacitance of the circuit, and we know the quality factor. Then what we want to calculate is omega naught, the resonant frequency, the resistance, the damping ratio, the natural resonant frequency. This is the exponential damping coefficient, and the damping ratio. So we need to start, with what are our formulas to do that? Well, we have LC, so we can easily calculate omega naught is 1/square root of LC. We've been using that for quite a while now. So our omega naught then is just going to be equal to 1 over, that square root of LC, plugging in, we get 2 times 10 to the 5th radian per second, or 200 kiloradians per second. Once we have omega naught, we need to still determine what our alpha, omega D, and the resistance are. Well, we can determine alpha, that's 1/2 RC, but it's also equal to our omega naught divided by 2 Q naught. So now that we know omega naught, so here, instead of using our old formula 1/2 RC, we can use it's 1/2 the ratio of the the resonant frequency to the quality factor, and we come up with 2 times 10 to the 4th Nepper per second. So that's our damping ratio there. If we, what else do we need to determine? We need to determine omega D, and we need to determine the resistance. So omega D, we have alpha and omega naught. We can plug into our old formula. That's also, or we can plug it into our new formula. As long as we know, once we've calculated omega naught and we have Q naught, we can get the rest of these factors. And we get that our natural resonant frequency is very, very close, right, to our resonant frequency here. And so lastly, we can calculate, what in fact is the resistance. Did we calculate the resistance? We didn't calculate the resistance. We could calculate the resistance from this, right? So exemplifying, of course, I do want to exemplify before we calculate the resistance that our Q naught, omega naught, RC. It's also omega naught divided by the magnitude of the capacitive reactance, omega naught divided by the magnitude of the inductive reactance. Well, let's go back and we'll calculate our R. R then is equal to Q naught divided by omega naught C, or equal to 5 divided by our 2 times 10 to the 5th radians per second, and then our capacitance, which is 0.01 microfarads, so that's 10 to the negative 8, 10 to the negative 8 farads. So what are we going to get there? We're going to get 5 divided by 2, or 2.5. We'll end up by times 10 to the 3rd. So we get 2.5 kiloohms. So if we increase this resistance, right, if our inductor and capacitor are fixed, if we increase this resistance, we're going to increase our quality factor, because we're still going to have that same forcing function here. That forcing function is still going to force that current, so that will increase that maximum voltage. It will also decrease our damping ratio, right? So it'll decrease our damping. It makes our circuit more underdamped, and more underdamped, that means our omega D comes closer to omega naught, and we have a resonance that doesn't have any, has fewer losses. All right, so that's it for this video.